Hello everyone, and welcome into another live stream. Bit of a weird stream, bit of a weird stream. Bit of a really weird one because you see, I'm having troubles. I think I'm having troubles with explaining the topic correctly. The topic being quantum physics, and because of that, I decided to start a stream in which I would explain quantum physics. Because quantum physics is not that hard of a thing, surprisingly. But I do believe that I'm having troubles explaining it correctly. Now, what do I mean by that? Well, you see, whenever you're explaining something, explaining to yourself is not really a good way to go because you already know what you are explaining, and so you have no idea what part is. What part has problems, right? You have no idea what is problematic. So, because of that, I have this right here, right now. I've set up this beautiful board for explaining stuff, and my plan is to get someone out there, anyone, to join the stream, and then I will explain to them quantum physics, and they'll tell me if they understand, if they have troubles understanding, and then I'll explain the rest. So, my idea is pretty simple. I'll just go on one known coder or Javid X9's Discord server. There are some really nice people, and I will ask anyone if they could help me if they could help me by listening to me explaining quantum physics to them. So, this could be scary, this could be terrifying, but I'll see what I can do. And I'll also obviously post everything onto my Discord server, because if anyone wants to join, then then more than welcome. Should I play some music? I probably should play some music, right? Yeah, let me just start checkups. Streams. If anyone would like to know to learn some quantum physics, I'm here. Alright, cool. Now, let me just go. This is really scary. New thread name quantum. Well, explanation. Bit of a weird request because it's not really programming related, but I've been studying quantum physics recently in order to explain it well in the video that I'm working on. But considering that the topic I'm bad at social interaction. that's why I want to be a YouTuber. A person who totally does not need any social interaction skills. Anyway, I'll explain the video that I'm working on, but but I have no idea if I can explain it well. If anyone would like to learn some basic quantum mechanics and help me understand, if I can explain, help me to get better at explaining it, I would be really grateful. And link to my stream. It's terrifying. All right. All right. I'll just wait. Graphic tablet to actually do everything correctly. So that's neat. And the moment someone joins, I will just go for explanation ultra low latency, which means it should be rather fresh. Caffeine in my vein, so everything is going right. I should also probably get some music. Bright 3 classical seems nice, right? YouTube. Copy. Classical music. Absolutely terrifying. In the meantime, I might as well start explaining it, actually. You know, in general. Because that might be a good idea. Alright, so, quantum mechanics. Hello everyone, and welcome to the course in quantum mechanics. So, the basic principle is really simple, that's at least the point, but it has a lot of weird looking maths. So, first of all, we should start with psi. What is psi? Well, psi is a function, but it doesn't look like a function. So, psi looks like this. This is psi. It obviously, some other people would draw it better. That's roughly how it looks. It is basically psi. Psi, that's just the symbol name for it, and it is a wave function. Wave function is just a function like any normal function. Except, well, yeah, it's like a normal function because it kind of can be any function. Because here comes the core, I would say, concept in quantum mechanics. When we have a particle, right, some sort of, actually let's draw a line for this. So, while drawing straight lines under pressure. There we go, good enough. Now let's say that this line is straight, okay? Let's just consider that it as a straight line. When we have a straight line, one very important thing to remember is that particles don't really have a given position. They don't have a position like every normal everyday object has. So for every normal everyday object, you have the position. So, you know, just some, let's walk in one dimension for now. So just some x coordinate anywhere on this line. We will have, let's say, a ball. Now we know that ball is over here, right? This is its x coordinate. In quantum physics, though, that's not how it works. Because particles are not just in some place, you have the probability of them being in a different place. So instead of particle being in one given place, you have the probability of it being in a different place. So for example, it is very highly probable that the particle will be over here, kind of probable that it will be over here, and ever so slightly probable that it will be over here. Based on that, what you can do is you can graph it so that this would be the position x, and this would be the probability of the particle being in a given place. So it would look something like this. Like this. Hey, how you doing, Elliot? Would you like to learn some quantum physics? Alright, Elliot. Now you're here, it's time. So, Elliot, welcome to the course on quantum physics. No, but for real, I do believe that quantum physics is not hard. Yeah, I do believe that quantum physics is not hard, and because of that, I do want to explain. So, let's start in the beginning with actually what I will explain. First of all, do you have any experience with calculus? Well, with advanced calculus, complex numbers, so mathematical basis. Don't worry about that. But do you understand? Like, do you have any background with calculus, with complex numbers, with probability? Complex a bit. So you don't have a lot. Yeah. Okay. So that's great. That's actually great because I do plan on explaining everything. Now here, this star x psi dx. My goal is to get you to understand this by the end. This very scary looking thing. In my opinion, I do believe that you will be able to understand this by the end. And by the end, I mean probably 10-20 minutes. Are you ready? Are you ready for this very wild ride? It'll be fun. Okay. So, I still haven't played the music. Should I play some music? Wait, alright. By the way, this should be from, if I'm not mistaken, this should be from Negative. But I do believe applied with you. Quite in. Okay. Right, I wait. In the meantime, I resolve my music problem. Also, finally, the analytics is showing me that you exist, which is it's rare. It's pretty rare. Usually, just for some reason, analytics just ignores you because you're French. That's what happens. In the meantime, I'll just draw a couple of things, get things started. So, that'll be the goal. There we go. That should be good. Let me check. Is it good? I have still absolutely no idea. Okay, so what I have to do is... Oh, you're ready. Okay, right now just give me a second because all I have to do is just... Alright, fine, we'll do without music. You can play music for yourself. Just, be more convenient. Anyhow, so... There we go. Instagram won't be that hard. Yeah, you are right. You are actually right. That is true. Integrals will not be that hard. Is my next chapter? Yeah. Solving them is not. Well, solving them is relatively more hard, but understanding them really is not. And in this case, you don't actually need to solve it. Anyway, here's how it works. You have psi, right? This is psi. Normally on the internet, it looks way nicer than I can draw it because this, yeah. Ariane thingy. Look, exactly. That's exactly. All right, cool. So you have psi, right? In case you would like to see how it looks actually, because normally it's way pretty. Actually, it's in the thumbnail. Normally it's more pretty, but yeah, I can't really draw. So that would be psi. Psi is something that's called a wave function. What is wave function? Well, I'm so glad you didn't ask. Here's the thing: when you have a particle, you can really in quantum physics. When you have a particle, it's different from a thing in a normal real physics world because that's quantum physics, that's the kind of core theme. You see, normally when you have an object, so when you have, let's say, a line, straight line that would represent the x coordinate. When you have an object, you can tell me exactly where it is. So for example, if we have a ball over here, you can tell me that this is exactly in this place, right? You can tell me its x coordinate. Normally we are operating in x, y, z coordinates. Yeah, but I do need to set up the base. So normally, teach me the math. Yeah, I'm getting there, don't worry. So you can tell me its x coordinates. Normally in the real world you have x, y, z, but obviously 3 dimensions would be really inconvenient here, so we'll start with 1 because that's simple. Actually, we will just do 1 because any more dimensions, I'll leave that for some other people more qualified. So we have an object, but in quantum physics, it is different because in quantum physics, you cannot actually tell the exact position of a particle, you can only measure the probability of it being in different places. So in quantum physics, if a particle has a really high chance of being in this place, little chance of being here, and a very little chance of being here, then what we can do is we can create a graph of probability of particle being in a place and how it's related to, like, probability to position. So this tells us basically the probability of the particle being in any position, right? So in here, it's far more likely that the particle will be over here than over here. And for example, over here, it has 0% chance of being there, right? That makes sense. That is a question, by the way. Does that make sense? Because, I have no idea. Yes, great. Grand. So this, as we can see, this is some sort of function, this right here. Some sort of function. That function is the wave function indicated by psi. So whenever you see this, psi, that's the thing, the probability of it being in any place. But over here, we don't have just psi, we have psi star x psi. So what's up with that? Well, here's the thing. Normally, we cannot use the only psi. We also have to focus on something looks like this, which is actually a very simple operation. Absolute value, I'm pretty certain you accounted it somewhere, but absolute value, is just looks like this. Yeah, exactly. That's absolute value. And obviously you know how squares work. Square root of x squared, exactly. And you obviously also know how squares work. But here's the question. If absolute value, why is the absolute value here? Why is it there? I mean, couldn't we just take the square? Because there seems to be no difference, right? Like this is still equal to 1, which is equal to, -1 squared. -2, that's still equal to 4, which is equal to -2 squared. 3 absolute value squared is equal to 9, which is equal to 3 squared. So why are we adding absolute values in that? Well, it's because the wave function is a complex function, which means that it also has the imaginary numbers. And the imaginary numbers, as you probably know, because as I said, you know the complex stuff. So imaginary numbers, which are a plus ib, I being the imaginary part. If you square I, you get the negative number, which is negative. And we don't want that, we want positive numbers. That's why we take also the absolute value, which then gives us 1. Now, this is really great, because basically all it does is just squares the function and makes sure that this will be a real and positive function. I don't know why it's so crooked, but real and positive. Yep. Not gonna lie, I had the same exact question, but this is it's surprisingly hard to find the answer for that, but I do believe it's just a notation thing. it's just a notation thing because all of the maths later on seems to indicate that this is just every single time when you look in line, it's always absolute and then square out. I don't. It's just a notation thing. Now it's time to get into something that you don't know about. At least I'm guessing, because I myself know if. Yep. You understand why? Oh, and then square that. Yes. Yes, exactly. Oh, that's well. Thank you then, because you explained actually something that actually makes sense. It's yeah. It's square root of x squared squared. Okay, that. Yeah. Okay, great. Anyway, now it's time to get into something that you don't know about, because I myself know a really big fair share of calculus, and I know a fair share of complex numbers, and I have never heard about that. So I'm pretty certain it's a weird, it's complex, it's a really weird thing, which is the complex conjugate. I know you heard about something like that. It is this star right here. So for value z, right? If you have a z, this would be its complex conjugate. Have you ever seen an operation like that? It's kind of like convolution except starts higher. It's not a complex, well, it is as it's ironically complex but not complex because it works with complex numbers but it's not complex itself. The complex conjugate is rather simple because when you have a number z that would be equal to a plus ib, then its complex conjugate would look like this: a minus ib, and that's it. You know this too? Okay, then I must miss because I've never seen that. I have no idea why. Yep. Far over it. Well, yes, that actually, yeah. There we go. Normally I won't do the bar because I won't do z, because complex, what we care is a different complex conjugate. You see, over here we can do equal, and this would be equal to psi complex conjugate times psi. That's why I don't usually do z, because it's not important, because we are talking about psi. And this is actually true. You can find out for yourself very easily that if you take that, this would be always real and positive, because if you take a, right, a plus b, a plus ib complex conjugate times a plus ib, then what you would get is a minus ib times a plus ib, and then because of there's minus here, we'll basically end up with a squared minus a squared minus ib squared. Obviously, you square the I cancels with negative, and you get a squared plus b squared. And considering that a squared is a positive number, has to be, because it's a real number squared, and b is a real number squared, that means both a and b are positive, and since we are adding them together, this will be positive. Yeah, ib squared, because yeah, because minus ib squared. So I and negative I squared and negative comes out. Yeah. And so we can just say that this would be so we can just use that. We use it because it's for some reason it's preferable. It's just preferable. So in quantum physics, let me just erase that because God knows I will need the space. So in quantum physics, this is the important bit, you see, and psi is kind of it's appearing a lot. Now it's time for the rest of this really fun equation, which is the probability, because right now what we've gotten is this. Hi there, David. The bit of a different stream today. Don't mind the quantum physics lecture for no reason. All right, now back to the good stuff. Over here we have explained almost everything except for the x, integral, and dx. So now it's time to explain it. As you obviously know, integral is just area under the function. Now integral, if it's unsigned like this, so this is just the area under the function. Pretty basic stuff, as we said. But this one is different. It has an x over here, two wave functions, and dx. Why? Well, it's because of probability. Oh my goodness, isn't it fun? In probability, you have something that I always forget what it's called. Let me check my notes. I hope everyone has a nice day. Be safe. Take care. You too, David. You too. Thank you for joining. Alright, I found it. Expected value. I don't know why I always forget what it's called. Expected value. What does it mean? Well, expected value is just kind of an average, I would say, in probability. So over here, if height represents probability, right? What would be, where's the x? This x right here. This would be this x. It's integral of wave function, which takes in x, then so it's integral of the complex conjugate of psi, destroying my maths. Listen, on this beginning, this is supposed to be intensive. Oh my goodness, is it the French thing? Is it a French thing where you all x is times? Oh, it's a French thing. X is where it's a French thing. Well, technically yes. France did a lot of, yeah, I know, but I know that. I do. But at the same time, you know. Listen. France definitely did less math than Polish. Look, I mean, take a look at this. In Poland, you have the Copernicus. Then, well, Copernicus, I was actually more of a physicist. No matter. Anyway, Fourier was French. Really? Fourier is actually a child. Fourier is actually great. Fourier transforms. Oh, it's a wonderful piece of math. Fourier is actually great. But back to this now. So we have this probability, right? We have this probability, and on average, what would be the expected position when you measure the position in here? So, particle can be in any of those points. Height represents height represents the probability of it being in that place. So what would be the average, the expected position? Well, probability tells us that the expected position can be calculated by taking the integral of the function of the probability density function. So integral of the probability density function times x. In this case, probability density is psi complex conjugate psi. That's the probability density function. So in our case, in order to calculate the expected position, that would be complex conjugate, psi complex conjugate, psi times x dx. And there we go. That is the thing in the top left corner. Now, Now, couple of important things to add here. First of all, what exactly is this expected position? This is my favorite. This is where things get on. Tell me, do you understand everything I've said so far? You except for maybe, well, actually, including. Do you understand? Is it clear so far, or is it because I can go back? There's no problem. But notation is killing me. Listen, you do know that I'm in open war with you do realize that I'm in open war with math notation, right? Like I made a video about this. Math notation sucks. You know, I if I could, I would just use LaTeX notation. And that's what you want me to do. I mean, I can. If you want me, I can use LaTeX notation. This would be int, then this. Actually, it will be int, psi, this star asterisks, psi x dx. There we go. Is that better? Alright, cool. Cool. Anyway, coming back to the thing. Now we are getting into the fun bit. And actual fun bit. I will find where you live. Okay. Listen. Because wait. There'll be time to, you know, threaten me later on. Alright, there is a selected time of day to threaten make it. It's in my schedule. But for now, let's get into the juicy bit. Are you ready? Are you ready to get into the really the thing that will open up everything? I'm waiting for an answer. I will not go on until you tell me that you are ready. Open my feed out. Alright, let's go for it. This tells you the expected position. Now, expected position in quantum mechanics is kind of like position in normal physics. What do I mean by that? You are probably familiar with the fact that there is something. Oh my goodness, that is bright. Wow. Yeah. Terrible. There we go. Much better. You are probably aware of the fact of something, a little tiny thing called velocity. You are probably aware of that. Really often denoted by v. You are probably aware of something like velocity, right? V. Its unit meters per second. It's quite quick to see. Well, meters per second. You know, the speed, as people call it. It's language barrier. Yeah, so basically meters per second. How many meters something traveled in how many seconds? For example, you know, let's say I can run at 1 meter per second. That wouldn't be that quick, right? But speed, velocity. Derivative of the position, exactly. Normally, people use meter per second, which is kind of off. In reality, they use basically the s over time, so the distance over time, which is wrong. In reality, the proper way to do it is to use, obviously, the derivative of this, the derivative of length, of distance, whatever, derivative of time. That's the proper way to do it, because then you can measure velocity at any given instant. And here comes the cool bit. How do you so this, basically what you can say here is that in order to measure the velocity, right, the speed, what you do is you take the derivative in relation to time of the position. That's normal physics. Right? That's just normal physics. Now quantum physics, so quantum physics, yeah. Normal stuff everyone loved and adored by everyone. Now in quantum physics, in order to calculate velocity, you take the partial derivative, I'll explain really shortly, partial derivative in relation to time of the expected position. That's why I said that normal position in classical mechanics, that's kind of like that's like expected position in quantum mechanics. So everything that you do in quantum mechanics is like normal stuff, except with the added thing that you don't know the position. You don't know the exact position. You only know you only know the probability of it being in any given place. Now, what's really cool about this is that for both of these things, it is actually kind of the same, except over here the units are like meters and stuff, and those units are massive. If you consider how many particles you can fit in a meter, then you soon realize that within a margin of error, right? This could be the same thing. This could be the same thing, but for things this large, you don't need to define it this precisely. So this is really similar. Partial derivative is here because of reasons. Because you cannot just... Well, because over here you just take the derivative of position of derivative time. In here it's partial because, you cannot take the complete derivative of something that looks like this. That will be only in relation to x. So it is, yeah, reasons. Mate, trust me, it's reasons. So do you get the thing? Because that's the most annoying bit. Well, not the most annoying bit, the most important bit. That's the most important bit when it comes to quantum mechanics. The fact that you don't have a single position, like your object is not in place A. Never did partial derivatives. Well, they are really similar. You just... actually, I can show you. It's really fun. Consider you have function f of x and y, right? And it will be equal to something like x squared plus x squared y squared, for the sake of simplicity, plus y squared, right? So if you take the partial derivative, did I do it right? How do you... Wait, it should be... Is this the right notation? I have absolutely no idea. Point is, if you take partial derivative in relation to x, right? No, wait, that seems very wrong. Yes, if you take the partial derivative of this, it would look something like this. So you treat the x normally, which means over here you have 2x, over here, and you treat the y as a constant. So you have 2x plus 2xy squared plus constant alone is just 0, so a 0. That would be the partial derivative in relation to x, and this would be the partial derivative in relation to y. So it would be x squared, a constant, which means a 0, plus x squared 2y plus 2y. That's how you calculate partial derivative. Let me just find notation so I can do it correctly. Partial derivatives notation. Oh, it was with f on top. I was right. Huh. Wait. There's so many different notations. Yeah. Well, not exactly unknown. You just consider the variable that you are not calculating right now as a constant. Of x, right? So x, that would be equal to 2x plus 2x times, this is a constant, plus, and constant by itself is a constant, times 0, so this would be just 0. That's the entire partial derivative in its simplest example. So obviously later on math happens, calculus happens, and then everything that's beautiful in the world, it gets destroyed by other examples. But now I can show. But now it's time to do some. Now it's time for me to show you some actual reasons. Because you see, I'm certain that so far you have wanted, but make it, are these functions normalizable? And obviously they are normalizable. I'm saying that was on your mind, right? You were thinking about if they are normalizable. I'm certain. Yeah. So here's the thing. In probability, one thing that's really convenient whenever you have a function, right? Bell curve. Let's imagine it's a bell curve. Close enough. When you have a function, right? F of x. In probability, one thing that's really convenient is to have the entire integral of that function, the area under it, right? It's really convenient to have it to add up to 1. If the entire area under the function adds up to 1, then it's really good for probability. Extremely, extremely good. For, as I said, reasons, once I don't want to, probability is a dangerous field, I don't want to get into that. Yeah, makes sense, exactly. Now here's the thing. When we have our function, right, this, so when we have our integral of psi complex conjugate x, actually not x, integral of complex conjugate psi dx, right? If we have our function, it probably will not add up to 1. It will probably not, because psi is just an almost random function, so it probably will not add up to 1. So what we need to do is we need to normalize it. What do I mean by that? Well, normalizing would mean taking the entire function, checking what it's equal to. For example, in this case, let's say it will be equal to b, whatever it will be. Or actually, let's use a real number because that would be probably better. 16. If it's equal to 16, it has to be equal to 1. In order to normalize it, we just have to divide it by 16. Because after we divide the entire function by 16, the entire function will be equal to 1. That's called normalizing. And actually, it is it's a really bad explanation. Normalizing functions, quantum mechanics. Let me solve one example for you really quickly. Not example, exercise. Give me an example. I can show what it's all about. Okay. Oh, can I get an easy example? Guess not. Alright, but makes sense, right? Cool. So, wait, do you understand normalization, or should I show you an example? No problems. All right. So I think I found an easier example. Okay. I'm decently certain I found it. So, let's consider a wave function. I don't know if that's enough space. Well, we'll figure it out. Let's consider a wave function, right? Because technically, wave function looks like this, right? Because it's a function. But in practice, for some reason, physicists really don't like to add this x here, so that's a function. Anyway, let's consider a function that would be equal to 0 if absolute x is greater than 1. And the actual function would be e to the ix 1 minus x squared. This is not an extremely easy example. So yeah, if absolute x is smaller or equal to 1, there we go, that's good enough. There we go. This would be our example. I already regret my decisions. So, are you ready to solve this? Actually, I think you will be doing something. Let's solve the example. So, what we need is from we need to solve this from negative infinity to infinity of complex conjugate times this dx. Right? Good question. Oh, yep. Good. Go for it. I don't have coffee. I already drank a cup of coffee. Is it e to the ix 1 minus x, or oh no, is it because I cannot write correctly because I'm using my hand and not normal notation? I can render it to you in LaTeX if that makes me happy. Quick LaTeX. I can render to you in LaTeX if you want. 1ix 1 minus a. Oh well, that's great. I'm glad it worked. I am so glad it worked. Oh yeah, that's festive. There we go. Is that good? There we go. Great. I should be doing this in LaTeX, not if I could figure out how to have like a live LaTeX renderer, that would be great. I would get all the ambiguity would disappear. Anyway, so we have this. Now here's the thing. If absolute x is greater than 1, then it's equal to 0, which means function will look very similar to this. Let's say we have 1 over here and negative 1 over here. Anything over on this side, right, is equal to 0. And anything over on this side is equal to 0. Don't you have a whiteboard? Oh, that would be good if I... Okay, I might have to set up something with a camera. I think I have a mixer somewhere. I'll see what I can do for tomorrow. Anyway, so we have everything on this side will be equal to 0, and anything on this side will be equal to 0 because of this, right? So what that means is if anything on this side will be equal to 0, anything on this side will be equal to 0, that means we don't have to solve the integral from minus infinity to infinity. We don't have to, because on this side everything is a 0, on this side everything is a 0, we might as well solve it from negative 1 to 1, right? Because it is just easier. It will be easier, it will be shorter, we won't have to worry about infinities and stuff. All of that messy stuff. Anyway, now what we need is the wave function e to the I x 1 minus x squared. And then what we need is we need to multiply that. That's the difference. Normal x is on the bottom and multiplying x is in the middle. That's the notation I was taught. Anyway, and we need to multiply that by e to the negative I, because complex conjugate, x 1 minus x squared, right? And dx, because we are solving an integral. I just realized you haven't done integrals yet, so this will be really fun. Okay, let's first solve this side, this normal looking part at least. So, oh, and yeah, one more thing. Actually, no, I will do it later. So, this will be equal to, and I will solve it on the left for reasons, and only on the right other things. So, first of all, we have e to the x I1 times e to the... I'm really rusty on this, and I need some coffee. Okay. a second. I'll be right back, okay? I'm sorry for betting on the stream like that, but I'll be right back. I just give me a second. Alright, I am back. Did you still hear me? Yes, great. Okay. So, when you have e to the ix, let's rearrange it in a different way. This is obviously still negative 1 to 1. E to the ix, this multiply by e to the minus ix, this way will be easier, and then let's multiply it by 1 minus x squared, and then let's multiply it by 1 minus x squared, and this is the exact same thing, which will be equal, I don't know, can you see this part? Oh, you can kind of see, I barely did. Now, e to the ix times e to the minus ix is equal to 1 because a to the b times a to the negative b is equal to 1 no matter what the thing is. So we have integral from negative 1 to 1 of 1 times, which means we might as well skip it, 1 minus x. I should write that more clearly probably because this looks like a y. There we go. Times 1 minus x squared dx, which is equal to 1 times 1, which will be, oh wait, negative 1 from 1 minus x squared. I always do it this way because I am a terrible human being. Plus x to the 4th, right? Which means dx, which means it will be equal to integral from negative 1 to 1 of 1 minus 2x squared plus x to the 4th dx. That is clear, right? I'm using exponential form for... Cool. Yeah, I don't know. I just wanted to add that because professionally, but then I want to film. But okay, it's fine. It's fine. That's who you. That's right. That's right. You don't have to flex or anything. Okay. Cool. We all know how to do basic math. I definitely know how to. I definitely know how to. Multiply exponents. I definitely don't have any problem with that. Anyway, now it's time for the integral. Now the integral goes in the opposite way as the derivative. When you have the derivative, so the derivative. Wait, no. Whoa, I did it wrong. Wow, that would be shameful. Dx. When you have a derivative of x to the n, then commonly known thing, n x n minus 1, right? Yeah, so, cool. Now that we have this is the integral, I mean this is the derivative, integrals go the other way, which means that integral of x to the n dx is equal to the other way, so divided by n if I'm not mistaken, x divided by x divided by n to n plus 1, right? Yeah, that's yes, right? Primitives. What? What you mean right now by isn't that primitives? Did I mess something up? Antiderivative. Yeah. Integral. Integral, antiderivative. Yes. English thing. Is it integral? This might be the word you are looking for. No. I'm thinking you're talking bond. Antiderivative. Yeah, that's what integrals are called. Antiderivatives. Plus constant missing. Yeah. I gladly noticed that. I wanted that plus C, but then I forgot that because you told me. Yeah, that's it. Yeah. Impossible. I mean, antiderivative is just an integral. What? How? Wait, what? How? Whoa. The derivative, I mean, the integral of a derivative, I don't know why I did it wrong twice. The integral of a derivative is just the original function. That's why it's called antiderivative. Wait. Is there an actual difference between an antiderivative or is there a difference between antiderivative and integral? Really? The collection of all antiderivatives of f is called indefinite integral of f. Maybe because it's integral sign. The function f is. Yeah, I mostly said thought, so wait. Let me check. Let me check really quickly. Oh, okay. I haven't. Okay, I got it. Okay. You want? Okay, you want to know the difference? It's. I mean, it. I guess. Okay, you want to know it? Yeah. Okay, here's the difference. When you have an integral of f of x, right? When you have an integral of f of x, which would be, let's see, x. When you have this integral, right? F of x, you can't see it because there's a day 52 in the top right corner. Elliot, you with me? I just want to double check. Good. Yeah, great. So when you have this this is an antiderivative. But this is also an integral. The thing is, integrals are also called antiderivatives when they are used on a function. The antiderivative is a function that when so this is an antiderivative whilst this is an integral, but they are equal. So the integral is when you are integrating a function, and antiderivative is the function you get from that integration. It's kind of like saying that 2 plus 2 is addition. Yeah, it's actually exactly that. It's kind of like 2 plus 2 is addition, but 4 is a sum. That's the difference. So integrals is kind of like 2 plus 2 addition, and 4 is a sum, just like this function is an antiderivative. I think the reason why you have two different chapters, one for integrals and one for antiderivatives, is because antiderivatives is when you are actually operating on a specific function. Majority of integrals, possibly yes. Possibly yes. Yeah. Mm-hmm. Because these are integrals. These are integrals. Maybe in the integrals it will be more about might be more funky examples, because these are very much toy examples. That's what I've written here. But now, yeah. So coming back to the thing, by the way, because I only got lost. Now you need to divide that plus 1. Yeah, so x divided by n plus 1, which means that this would be equal to this is the x to the 0, which means x to the 1. So x minus 2 times x to the second. This should be plus 1, right? I think I am right here. So x should be plus 1, and then so x to the second, which means should be x to the third. No, because this is the 0. Oh, so this should be 2/3 x to the third. Make that 3. There we go. The third. Yeah. Yeah. My brain is very slow. And x to the fifth by 5. And over here we have 1, -1. And so this will be finally equal to this minus this. Oh, that takes up so much space. Oh, I don't have any more left. Well, then we will have to do it over here. We will get, oh boy, this will be 1 minus 2/3. That's it. Plus 1/5. That's great. Amazing. Wonderful. Minus -1. Minus, this is 2/3, so nothing changes. So minus negative plus 2/3 plus 1/5. No, minus 1/5 over here. Minus 1/5. Which would be equal then to this minus. Alright, so this would be equal to basic addition. Let's see if make it can. Let's see if make it can do simple addition. 1 minus 2/3 plus 1/5 plus 1 minus 2/3 minus 1/5, which basically means plus 1/5, which basically means what we get is 1 plus 1, 2, plus 2/5. The fact that I'm struggling with this 16/15, I'm glad that I have someone in chat who is better at math than me. 16/15. I trust you. I believe you got it right, because let's be real, I got that wrong. Anyway, I cheated. Oh no, how dare you. But now the important bit. Got 3 hours of maths today. Oh boy. Now, oh no, I've only got an hour. Ain't no way I do. Anyway, now the important bit. You know what the important bit is? The very important bit. This is equal to 16/15, right? Right? No, it's just equal to 16/15, right? Oh, yeah, it is. But as I said before, this has to be equal to 1. So we need to normalize that. How do we normalize it? Well, the way we do it is we imagine that over here we have a variable a. Variable a which we'll use for normalizing. This would be actually a e to the ix times, in brackets, 1 minus x squared. We give it normal pills. Oh, government. Anyway, which means that our a variables also have to be over here, a, e, and over here, a. We have, because we use that function twice, which means over here we will have a squared, which means this would be equal to 16/15 times a squared. You typed that in chat faster than me, which might mean that you already knew that. Why do you know that? Why do you know that? Now tell me. Type that in chat before I wrote it down. Elliot, are you secretly a quantum physicist? Okay, yeah. Then, okay. If you got the of that, I put into place. Then yeah, that's correct. A squared, obviously. Yeah, exactly. So in here we have the 16/15, which is the integral solved, times a squared, because we can just take the a's out of the integral over here. Now, in order to normalize it, what we need is 16. We just do now we do the actually really hard math, which means a squared times 16/15 has to be equal to 1. Now this is difficult, obviously. so yeah, mate, this is actual hard maths. Let's be real. So what we obviously I'm doing this a squared divide 1 by 16/15, which basically means 15/16, if I'm not mistaken. Square root both sides, which means a is equal to square root of 15/16, which means that in order to normalize this, we need this to be equal a square root of 15/16 e to the ix times, in brackets, 1 minus x squared, close bracket. There we go. And so now you understand. Oh my goodness, I did not realize how loud it was. Let me just move away for a second to actually scream for comedic reasons. So now you hopefully understand how normalization works. It's 16/15. No, it is 15/16, because when you have a squared 16/15, right, is equal to 1. So you divide both sides by 16/15, which means that over here you are left with a squared, and this is equal to 15/16. Because when it's actually 1 divided by 16/15, which is equal to 15/16, because when you have a 1 it just flips, so 15/16. And then a is equal to root of. Yeah. It's basically it's a fraction of a fraction. It's not confusing at all. Anyway, now you got the normalization, right? Right? You get what I mean. You get what normalizing is. You get the process. So now, cool. Now you get what normalizing is. Let me ask you a question. Are you certain that it will work? I mean, mathematically, so far it seems that we can normalize, but should we? What if it doesn't work? What if adding a variable here breaks the entire thing? Well, we can check for that really easily. First of all, we'll check it using the Schrodinger's equation. Oh boy, now we're getting into good stuff. So first of all, we'll check it in the Schrödinger's equation, which means I h hat partial derivative in relation to time of psi is equal to negative h hat squared divided by 2m partial derivative of psi, but this is squared partial derivative of psi in relation to x plus v, which is, if I'm not mistaken, the potential energy function times psi. And now it's time to check it. What we did there is we multiplied the wave function, but by the constant, right? So now we multiply every single wave function by the constant. We multiply it over here, we multiply it over here, we multiply it over here, and this equality is still true. Because in math we can multiply both sides by a constant. This plus right here, this plus is here, which means if we had something like plus v over here, it wouldn't work, because after we multiply every single wave function by a, this wouldn't be equal, because over here we're missing an a. But every single part has a psi, which means that after we multiply it, everything is correct. Can you see it, or should I do it, or should I do it normally? Partial derivatives look like a 6. Because they are 6s, I did this one wrong way. That's why it looks like a 6. Now it should look less like a 6. That's psi, yeah, x, and plus v psi. Do you get the idea of, multiplying both sides by of the fact that in order to normalize the function, we need to multiply every single psi by a. Get that? Not quite. Okay. It's understandable because, not gonna lie, I myself am understanding it less as I speak. So, because of the way it's really messy, my explanation. But let's do it. Let's do it again. So, what we have here is Schrödinger's equation, which has very different meanings. It's basically magic. It's basically like a spell. It's a magical spell. Someone of my expertise should never explain it because, oh my goodness, am I going to get things wrong? H hat squared divided by 2m, and then the second partial derivative of psi. Oh wait, shouldn't this be x? No, x should be over here, yeah. Plus v psi. So this is our equation, right? Clear the board, I will clear mine. This board is looking really fun though. This looks like I'm crazy and I enjoy it. Alright, so this is the Schrödinger's equation. You don't have to know anything about it except for the fact that it exists and is true. Now, when we have an equation, like for example, let's create a simpler example. Let's say that we will have something like c times d plus e is equal to c times f plus h. Let's say that we have something like this, right? Now over here, well actually this is incorrect. This should be cd. C times d is equal to c times f plus c times h. Let's say we have an equation like this, right? It's rather simple. Over here, if we multiply both sides by a, we get a c times d is equal to a c times f plus a c times h. No, that's not what I mean. I mean, I get that you can divide both sides by c, but that's not quite what we're going through right now. We can multiply both sides by a and the equation would still hold true, right? If we multiply both sides by a, the equation will still hold true. Yes. Now, look what happens if we multiply only one variable by a, which means if we multiply d by a times equals a. If we multiply d by a, it is no longer true, because cdA is not equal to cf plus ch. Obviously, we are considering a is, a is different than 1. This would no longer be equal, because we multiplied one thing, but the rest is not multiplied, so this is wrong. Which means we cannot just randomly multiply D by A, because it just wouldn't hold true. Is it clear, or did I use way too many variables? Because now I'm looking at it, it's... Yeah, and considering that C is not equal to 0, obviously. But here's the thing. So we cannot multiply D by A, because it would just... YouTube makes that... Oh, is YouTube compressing it? Oh, no. Actually, not quite. Well, it is compressing it, but... Nah, it's good enough. Yeah, it doesn't work anymore. It's not equal. But look what happens if we multiply C by A. This is times equals. It's a programming notation. It's good enough. If we multiply C by A, then what we get is C D A is equal to C F A plus C H A, which is true. That's just like multiplying both sides by A, which means that C can be multiplied by any variable, and this equation would still hold true. Yes, and the exact same thing is happening over here. We can multiply psi, right, by any variable because we can multiply by every single variable because there's no difference between multiplying it by any variable and multiplying the entire thing on both sides. So if we multiply, it is the exact same scenario. This is the CD, this is the CF plus CH. There is a lot more things going on, but but it's the exact same scenario. That's why we can multiply the psi function by a constant. I shouldn't say variable. All of the time I meant constant. Is that clear so far? This is actually this is a lot. It's very much, yes, it is cool. So that's a lot. But I'm definitely certain. I know what you're thinking right now. I get it, but make it. Can you normalize with time evolution? I know that. I know that that's what you're thinking. So don't worry. We will check if we can normalize functions when with time evolution, because I'm certain that's what you wanted to know. So let's get ready. Okay, are you ready? Yep. I should probably. I might. Do you have quantum physics? That would be sick. I might be spoiling this, but it's. If you wait, will you really? Oh, that's so sick! I'll be spoiling your quantum. Oh, that's great. Oh, that's fantastic. Oh, that's amazing. I am so glad that. I am so glad. Let's go for it. All right. So now, with the time, when it comes to time evolution, oh, this is amazing. When it comes to time evolution, I will not write it down. I don't know. I shouldn't write it down because it's a lot. Instead of that, I will show you money animation that I made, the manimation that I made because I was working on the video. I still am working on the video for this. That's why I made the poll. No, well, not quite. I made the poll on my Discord server asking if if I should postpone the video because right now it is nowhere near being done and I have to upload it in 2 days. Quantum physics is that's surprising a lot of stuff to explain. Anyway, this is our good friend the equation. The admission, I'll take a little break for 4 p.m. listen, I think this could actually be this could actually be it. So, all right. So we have the derivative of time for this, right? That means time evolution. And after we put it in there, we get the partial derivative because it's a partial derivative at this point. And after that, we can apply the partial derivative. After we apply the partial derivative, if we take the Schrodinger's equation, that's the Schrodinger's equation, we can transform it. So basically, IH transformed by IH to get this. Put it all to the side. It will come in handy soon. Then transform it like this. Put it to the side, and now we have the partial derivative of psi with relation to time, which is also over here, and partial derivative of psi complex convolution in relation to time, which we can find over here, which means we can just replace those. We can first replace this one with this equation, and then we can replace this one with this equation. And after we replace all of that, what you might notice is that over here we have negative this. Well, you have a lot of stuff. If you simplify it, it looks like this, and if you simplify it again by taking out this, you get something that looks like this. Then all you have to do is just, I think, solve the integral, and that's what you get. And where are we now? Wait, where are we now? What is the end, by the way, of the animation? I messed it up, because that certainly does not look like the end of calculations. That, I'm pretty certain there's not the end of calculations. Well, it ends over here, that's the point. And the point is, no, you can do time evolution and thing. So yeah, that was my TED talk about quantum physics. How are you feeling? How are you feeling about this? Nice, nice indeed. Thank you for being in my. Thank you for being here, listening to my TED talk. I just had to share this with someone, otherwise I would not be well mentally. Might have spoiled a bit of this year program for me. Oh, next year. Listen, tune in tomorrow for more quantum physics because I am still in the middle of researching. There is a lovely, if you like to, if you want, I don't know why would you want that, but if you want, I want, sorry, no worries. I did ask that as a meme. Oh, you still have exams. Oh my goodness. I thought you just. Oh, I thought you. Last one was the last one. Philosophy exam. Oh, like that. Ah, you'll be fine. I believe in you. I believe in you. Yeah, yeah, that does. Yeah, you'll be fine. Wait, that's the last one. That's great, actually. That's great. Last exam. By the way, sorry for being selfish, but please vote in the poll because I have no idea what to do. No, actually, already voted. Never mind. All right. Well then, I will not be taking up any more of your time. I'll go back to I'll go back to working the videos, and I'll see you soon. Thank you, Elliot, for keeping me mentally sane. Yeah, good luck and goodbye to you too on your exam. See ya. Pascal was French too. I thought you were gonna say, remember, the derivative of e to the x is e to the x. Anyway. can you stop listening? You said the Fourier was French. That blew my mind. Fourier is a big one. Fourier transforms are amazing. It is a he's a French mathematician. Look, actually, Laplace. Well, Laplace is also kind of important, but no one cares about that. Oh yeah, 40 was French. Oh, that's so sad. I mean, it's great. It's great. I think I should save this. It's actually way less than I thought it would be. Actually, way less. Genuinely, way less than I thought. I think a little. All right. Well then, that'll be it. Thank you, Elliot, once again. Thank you. And I'll see you soon. See ya, or whatever they say in France. Bye. Oh wait, I should do no goodbye. Thank you for watching, and have a great day. Bye.